Um, and all these systems, they use cryptographic building blocks, but they use many instances of those building blocks, and they use, of course, for each instance, they use, for example, many ciphertexts, and they use this building block a lot of times. And to clarify and to avoid misunderstandings, let's say our axiom is that we want the system to be secure as a whole, which means that all these many instances of the schemes are secure. So we're not satisfied if one of them is insecure, we want all of them to be secure. Let's say this is what we strive for. Then what we would like to have, of course, is something like a security guarantee that says the only way to break the whole scheme in total, all of the instances, is to factor, say, a 2000-bit number. What we actually have for most systems in reality is that the only way, if we have some security guarantee at all, is that the only way to break the scheme in such a setting is, say, like a slightly smaller number. It's like 2000 minus f of n bit number, for instance, where f of n somehow depends on, well, what problem we have, what the quality of the problem is, and how many users we have in the system. That's the bad thing. So in order to make a reasonable bit length recommendation, we need to know the scenario in advance, the size of the scenario at least. That's not satisfying. What we would like to have is, we would like to have tight security in the sense that the only way to break the whole scheme, independently of the number of instances, we want to have that this is guaranteed in the sense that the only way to break the scheme is to factor a 2000-bit number. Okay? So what our results are, we present tightly secure in the foregoing sense, tightly secure and compact signature and encryption schemes. And for the rest of the talk, I will focus on the signature scheme. And to give you some kind of context of where this is operating, so there are already tightly secure signature and encryption schemes. And for signature schemes, this is a small set of results, representative set of results. And the problem with these is that you have to choose if you want to have a compact description of the scheme, which means that, for example, in the signature is that the signature itself, the public key and the public parameters, all of them should be small. For example, this is the case for strong RSA-based schemes, or those based on strong Diffie-Hellman. Or if you want to have security from a more or less standard assumption. Of course, it's debatable what exactly a standard assumption is, but let's say that like a Q assumption, like a strong DDH assumption is not standard, or an interactive assumption is not standard, but let's say, for example, decision linear is a standard assumption. That's, of course, some subjective classification. And in this work, we'll achieve both. We'll get compact signatures, and we'll get those from a standard assumption. And all of this, the whole table, of course, it's about tightly secure schemes. Of course, there's very compact signatures from RSA, but they're simply not tightly secure. Okay, to recap, what's a signature scheme? It's just two fixed notation, basically, right? So we have three algorithms: key generation, we have signatures, and we have verification. And it works in the usual way. You use the secret key to sign a message, and you use the verification algorithm and the public key, the verification key, VK, to check whether a signature is valid or not. And of course, we want correctness in the obvious way. What do we want to achieve is, let's say, for the time being, that we only want to achieve tight security in a one-user sense where we have many signatures. So we have a security experiment, the usual existential unforgeability experiment, and we have many queries for messages or for signatures from the adversary. The adversary gets signatures, and then at some point the adversary tries to forge a fresh signature for a fresh message. So it's not strong existential unforgeability, it's just existential unforgeability. Also, the message has to be fresh. And we want that this is, of course, an unlikely event, that the adversary succeeds. We restrict to that case because if the scheme is Grotze-High compatible, which is means it only uses algebraic operations in a kind of black box way, in that case we can convert it to a many instance and many user encryption and signature scheme. So that's why we focus on this particular setting here. Okay, our starting point for constructing such a signature scheme is the IBE scheme of Chen and Wei from Crypto 13. And we'll interpret this IBE scheme using Naur's trick or Naur's interpretation simply as a signature scheme. And if you do that, then signatures in this scheme have the following form. they consist of two group elements, and one of those group elements is basically, well, you can think of this just as a funny way to encrypt X, and X is the secret key, basically. So X is a group element, it's a secret key, and you find a way to encrypt this such that you can check whether you're dealing with an encryption of X. And the rest is just generated from a random distribution that somehow allows you to perform this particular check. And we'll get to see what the effects of this particular form are in one of the next slides. Okay, and how does the security proof in this setting work? So the security proof works basically by randomizing the secret that is encrypted upon each signature. So you can view the signatures as an encryption of the secret, and what you do during the security proof is you try to individualize or randomize this secret depending on the message. So you start with X, which is just a constant thing, a secret in the secret key, and you end up with a random function of the message, a completely independently random function of the message. Of course, this only happens in the security proof. And if you're at that point, then if the adversary tries to forge a message, then he would have to predict a random function on a previously unqueried input. And this means that the adversary basically has no chance to win the experiment. So once we're here, it's basically over. We have won. And how does this proof work? It's a hybrid argument where in each step we randomize this secret that is kind of encrypted in signatures a bit further. So we start with just X, and this can be interpreted, because it's a random value, as a random function evaluated on the empty bit string. And then during using a magic step, basically using a sequence of magic steps, we just add additional dependencies on the message bits that are to be signed. So we start by, making this individual and making this dependent on the first message bit, then on the second two message bits, on the first two message bits, and then so forth, until we end up with a secret that is encrypted here that is completely dependent on the full message. And then, again, we have won. Okay, but let's zoom in a bit more and see what that magic adding dependency step is in Chen and Wee scheme. So basically, their proof works as follows, and then it becomes also clear why we can deal with many instances or many messages, many signatures at the same time. So let's say we want to add one more dependency on the jth bit, and we've already established dependencies on the first j-1 bits. So again, we basically give out, or we output to the adversary, we output a lot of such encryptions, and we want to randomize them further. That's the deal. So how to get there? First of all, it's kind of a thought experiment where we divide, or where we partition all messages, all possible messages, and all messages in particular that we consider for the adversary, that the adversary gives us. We divide them into into one of two sets. So we partition the set of all messages into two, and depending on the jth bit of the message. So all messages with the jth bit being equal to B go into the lower half, and the other ones into the upper half. So once we've done that, that's basically, so far it's just a thought experiment, but in the second step, we embed a computational challenge. That could be like a decisional Diffie-Hellman challenge, a decision linear challenge, something that can be re-randomized, so that we can embed many challenges into many of these group elements H from the definition of this funny encryption scheme here. We embed a computational challenge into all those messages, or into all signatures for those messages in the black part, or in the semi-black part here, which means we randomize half of the messages, and this is done algebraically by just randomizing one particular hi, b value here. So that's one group element that is used to generate this hi, b, and that's in the public key. So we can do this using basically little effort. And the effect of this is that this secret value that is encrypted here is randomized for all those messages which we have considered in this case. And for the other part, for the messages that we did not touch, we have some property that we can still check whether the adversary has given us a valid forgery or not, because we have to enforce this new definition of valid signatures not only on those the encryptions that we give to the adversary, but we also have to enforce that on well-being on the forgery that the adversary gives us. So this third step is necessary in order for us to be able to still be able to judge whether the adversary has won. So we basically divide everything in two halves, we change one half, and we hope that the adversary at some point gives us a forgery from the other half, which we can deal with, basically. Okay. And in the end, what this means is that we have randomized one of those hi, b's, which results in a freshly random value z here. And in the end, this means just we have decoupled those two halves, which means there's an additional dependency on the jth bit. Okay. So the thing is that this requires n hybrid steps, where n is the number of message bits, and it's a small reduction loss, but it's not dependent on the number of queried messages, it's just on the message bits. But also, it means that in order to embed our challenge in the way I just sketched, we need like 2n slots in the public key or in the public parameters to embed this challenge. We have to have a case, basically a case distinction for each message bit, and that costs us a lot of group elements in the public key or in the parameters. You can push them into the parameters, in fact. Just a side note, this basically can be seen as an additional variant of the Naur-Reingold pseudo-random function. So also the proof technique is pretty similar. But in this case, it's a public key and an additive version of this, and so it costs us a large number of basically of group elements in the public key. So what we do now is basically find a way to hide this partitioning, or to find a way to have a much more space conserving version of this partitioning. So we implement the same strategy, but we just take a different way of partitioning the set of all messages into two subsets. So if you think of maybe a more algebraic way, then we can, first of all, we can hide this inside a Grotzer-Hall proof. So I won't go into the details what the benefits of this exactly are, but maybe it becomes a bit more obvious in the description of the scheme. And we're looking for a predicate that first of all is kind of algebraic, so that's the yellow part, and it should be a way to partition the message space into two sets, which are approximately at least half. So what our predicate is simply quadratic residuosity, but modulo the group order, which is in this case, it's a prime. So observe that the set of messages, if I interpret this as just values modulo q, then about half of them are squares. And if you forget about the zero, then exactly half of them are squares. And the other ones are non-squares. So this is, as a predicate, partitions the set of all messages into two halves, right? And if you want to do not only one partitioning, but many partitionings, so you kind of can establish a random function on the messages by querying all of the partitionings and where the message sits in each partitioning, then you need to just randomize this predicate. So what you do instead is you can not take the fact or the property whether a message is a square, but you can ask for an affine function of the message and ask if this is a square or not. So what this results in is then, in the end, a signature scheme which superficially looks very different from Chen and Wee scheme, but in the end, the concept is pretty similar. So we have a funny encryption of X. This is the secret. And then we have two Grotzer-Hall proofs. So the first one is for partitioning the message space, and it says that either this is, I can decrypt this basically, either I know the plaintext of C, so this is something where doing the security proof, we can pull off a Naur-Reingold double encryption kind of trick, or, and this is a trapdoor for the simulation to change the messages that are in the other half of the partitioning, or f of m is a quadratic residue. This is kind of the trapdoor for the simulation, basically. And the second one is a bit boring. It just, this is something which initially guarantees that this is really an encryption of X, but as soon as we're in the proof, we're going to simulate that proof, and we don't use any simulation sounders or anything, but we're going to get rid of this pi2 very early on in the proof. And the proof gradually transforms signatures into this form that we know from Chen-Wee signatures or Chen-Wee IBE schemes. Okay, that's basically it. And the proof is pretty similar to the Chen-Wee proof. I won't go into the details of that, but the partitioning is very different. So I'm already getting to the summary and to the applications part. So first of all, the reduction is also tight. It loses, well, tight in the sense that it doesn't depend on the number of queries, but it still loses something in the security parameter, about 12n, where n is the security parameter. And the efficiency is, well, it's not really practical, right? So it's not something you would actually want to use, but it's maybe there's a bit of potential for optimization there. It's at least not completely out there, right? So signatures have 25 group elements. That's not exactly competitive, but it's also not obfuscation. Sorry. Okay, and this is suitably algebraic, so we can convert it into a tightly secure public key encryption scheme with, well, it has ciphertext have a few more group elements, but not many. It's 30, or no, I forget how many exactly, but not so many more. Okay, that's basically it.